In today's digital landscape, data is one of the most valuable assets a business can have. Every interaction, such as a customer making a purchase, visiting a website, or posting on social media, all of these generate data that businesses can use to make better decisions. This is chapter 1 of a larger course titled Introduction to Information Technology. And besides the introduction itself, the overall course is designed to bridge the gap between technical IT concepts and the practical application in business operations. In this video chapter, we will take a comprehensive look of how data is managed and used in a business context and how it is fundamentally processed by computers. We will begin by exploring data from a business perspective, covering key topics such as data types, where we'll understand the various forms data takes within an organization, data lifecycle management, which covers the processes involved in managing data from creation to deletion, business intelligence, where we will see how data is transformed into actionable insights for decision making, data governance, which ensures data quality, security, and compliance, and data formats, where we will familiarize ourselves with the common data interchange formats. And then we will transition to the technical foundations of data processing, focusing on binary and hexadecimal systems, which will help us understand the core languages of computers. Encoding standards will show us how characters and symbols can be represented digitally. Multimedia data storage will cover the principles behind storing images, audio, and video. And in units of data, we will understand the scale used to measure digital information. Let's start from the very beginning. What is data? Data is any recorded fact, measurement, or observation. Data comes in many forms. Numbers and text might include customer purchase histories or financial reports. Image, sound, and video are also data. These can be product catalogs, recorded customer conversations from support helplines, or security footage. Even sensor readings from smart devices like temperature levels in a factory fall into this category. However, raw data by itself is invaluable. It needs to be structured, processed, and analyzed to reveal meaningful insights. In business, data comes in different forms, and understanding these types is essential for effective decision making. First, we have structured data, which is highly organized and stored in tables, spreadsheets, or databases, making it easy to search and analyze. An example would be sales records in an Excel file where each row represents a transaction with specific details. Then, there's unstructured data, which doesn't fit neatly into rows and columns but is rich in insights. Examples would be customer reviews, emails, or social media comments, which don't have a predefined format, but they can help businesses understand customer opinions and trends. As companies grow, so does the amount of data they generate. This leads to big data, which are massive, complex data sets that traditional databases struggle to handle. To process and analyze big data, businesses use specialized tools like Hadoop and Spark, enabling them to extract valuable insights from vast amounts of information. With so much data being generated, businesses need a structured approach to managing it efficiently. This is where data lifecycle management comes in, ensuring data remains secure, accessible, and useful from the moment it's created to when it's no longer needed. First, we have data creation. This is when data is generated from various sources like applications, online transactions, and IoT devices. Next, data storage is where the collected data is saved, either in structured formats like databases or in unstructured formats like data lakes or file storage systems, including cloud-based solutions. Then comes data usage and sharing. This is where the stored data is accessed for reporting, analysis, or decision-making, allowing businesses to gain insights and drive actions. Over time, data that is no longer needed for daily operations moves into data archival, where it's stored securely for compliance, legal, or historical purposes. Finally, when data is no longer useful or legally required, it goes through data deletion, ensuring secure removal to free up storage and reduce risks. By following this life cycle, businesses can maintain control over their data, ensuring it remains both valuable and compliant. Managing data efficiently is important, but data alone does not create value. Businesses need to analyze and interpret data to support decision making. So let's take that well-managed data from the data life cycle and see how we can transform it into powerful business insights using business intelligence or BI. Simply put, BI is all about taking the data we have diligently managed through its life cycle and turning it into strategic advantage. We move from just storing and securing data to actually using it to make better decisions. And here's how we can make the leap. We start by leveraging the data we have collected and stored in the data lifecycle, but to use it for BI, we need to prepare it, or in other words, get it ready for analysis. This involves processes like ETL or ELT to clean, standardize, and integrate data from various sources. ETL is extract, transform, load, and ELT is extract, load, transform, the difference being at what point do you want to transform the data. ETL transforms data before loading it into the target system, while ELT loads raw data first and transforms it within the destination, which is often a data warehouse or data lake. To make sense of our data, we need to organize it. We can create data models using star schemas and snowflake schemas to structure data for efficient querying and analysis. We also need to choose the right storage solutions such as data warehouses for structured data or data lakes for diverse data types to support our BI initiatives. We can use statistical methods, data mining techniques, and analytical tools to uncover hidden patterns, trends, and insights within the data. Examples of analytical tools would be Microsoft BI, Tableau, and Excel. These BI tools enable us to create interactive dashboards, charts, and graphs that make complex data easy to understand. Finally, we can use these same BI tools to create reports and share our findings with stakeholders, enabling them to make data-driven decisions. This leads to actions that drive business outcomes such as improved sales, optimized operations, or enhanced customer satisfaction. And for businesses to make informed decisions, their data must be accurate, secure, and properly managed. Data governance is the framework that ensures data is handled responsibly throughout its lifecycle. And data governance is put into action through rules, policies, and standards that guide how data is managed across an organization. Let's start with rules. Rules define how data should be handled in different scenarios. They help businesses answer key questions like who owns the data. So for example, the sales team may own customer contact details, while the finance team may own billing records. Who can access or modify this data? So for example, only HR should be able to edit employee salary information. And how should this data be classified? This may include labeling customer data as confidential. Next is policies. Data policies provide guidelines for ensuring consistency, security, and compliance. They act as a company-wide agreement on how data should be collected, stored, and protected. Common data governance policies include data privacy policy, which defines how personal data is stored and protected. For example, following GDPR, the General Data Protection Regulation or GDPR is a European law that sets strict rules on data collection, processing, and user consent to protect individual privacy. We can have a data retention policy establishing how long data should be kept before deletion. For example, financial records may be required to be retained for 7 years. And we can also have an access control policy which determines who can access certain types of data. So for example, financial data may be restricted to senior management only. Let's move on to standards. Data standards define how data is formatted, labeled, and stored so it remains consistent across the organization. This prevents data duplication, mismatches, and errors that could impact business insights. Some examples of common data standards could be naming standards. A company may require customer names to be recorded as first name, last name. So for example, John Smith and not Smith John. We could have data formatting standards. All dates must be recorded in a certain format, for example, YYYY-MM-DD. And we can also implement master data management, which ensures that business data, for example, customer records and product details, remain accurate and synchronized across all systems. Popular MDM software solutions include Informatica, MDM, SAP Master Data Governance, and Microsoft Purview, which help organizations maintain data consistency and quality. By implementing strong data governance, businesses can improve data quality, reduce risks, and build trust in their data-driven decisions. Next, let's break down some of the common file types you will encounter when working with text and numerical data. First is CSV, which stands for comma separated values. CSV files are great for storing tabular data where rows and columns are separated by commas. They are simple and widely used in data analytics, especially when exporting data from spreadsheets or databases. Let's take a simple example of a product with the following details as on the slide. So we have product ID, a product name, and a price. In CSV, it would look like this, where we have a header row followed by data rows. And header rows could be optional. Next, text files are used to store plain, unformatted information. It's the simplest file type where data is stored as raw text. Use it when you just need to store some basic information, such as simple notes or logs. The same example in text would look like what we have on the screen. This is just one format. Textual data could be in any format though. Next is JSON, which is short for JavaScript Object Notation. JSON is popular for data exchange, especially in web applications. It stores structured, hierarchical data, often in the form of objects and arrays. If your data has nested relationships like product details with categories and prices, JSON is a great choice. Our previous example in JSON would look like this, where the product details are nested inside a product object. And we also have XML, which stands for Extensible Markup Language. Like JSON, XML can be used for storing structured data, but it uses tags to describe the data. It's more detailed in JSON, but is still widely used in web services and configurations where data needs to be shared between systems. We have an example of the XML version of our data on screen. Similar to JSON, the product details are nested within the root element product. Each piece of data is enclosed within a pair of opening and closing tags, making it easy for both humans and computers to read. Now, let's get a bit more technical and understand how computers actually process and store this information at the most fundamental level, which is binary data. Computers don't store or process information the way we do. Instead of words and numbers, they rely on binary, a system made up of just two digits, zeros and ones. Everything that a computer processes, from text to images to videos, is ultimately converted into binary. The other two numerical systems used in IT are decimal and hexadecimal. Each system serves a specific purpose and is used in different scenarios. First, let's look at the numbering system that we are most familiar with. Humans are accustomed to thinking about numbers as a combination of values from 0 through to 9. This is the decimal numbering system, which has a base of 10, since it can be represented by 10 distinct symbols. Let's break down some of the decimal math. Counting from 0 to 9 is straightforward, but we are restricted to 10 numbers. When we want to represent the next number after 9, we place a 1 to the left of the first digit and reset any digits on the right to 0. And this results in the number 10. And now we can carry on further. 11, 12. Notice the column headers on the top. The rightmost column represents the ones place, which is 10 to the power of 0. And the next column represents the tens place, which is 10 to the power of 1. So we can write the number 12 using the powers of 10, that is 1 times 10 to the power of 1, plus 2 times 10 to the power of 0. As we add more digits, we can expand the range of values we can represent. For example, with 2 decimal digits, we can represent 100 unique numeric values from 0 to 99. And we get 100 for the range of values by taking the base and raising it by the number of digits. So the base is 10, and we want to find the range of value in a 2-digit number, which gives us 100. While the decimal system is intuitive for humans, it is not inherently compatible with computers, which are designed to understand binary digits. In the binary numbering system, a bit, which is short for binary digit, is the smallest unit of data in a computer. It can hold one of two values, 0 or 1. The binary system is based on these two possible values and is referred to as the base 2 numbering system. For example, 0 in binary is the same as 0 in decimal, and 1 in binary is the same as 1 in decimal. Let's look at how to count in binary. To count one number up in binary, you place a 1 to the left of the first digit and reset all the digits on the right to 0. We get 1 0. This is equal to 2 in decimal. We can represent this 2-digit binary number in an 8-bit format by filling in the remaining 6 empty spaces on the left with zeros. So we get 00000010, which is still 2 in decimal. 8 bits, which is also known as a byte, can store a range of values given by raising the base of 2 by 8, which gives us 256 unique values ranging from 0 to 255. We can convert a binary number to a decimal number. Let's walk through an example using the binary number 11101110. Remember this example where we expanded the decimal number 12 using its positional values? We can use these same rules to convert the binary number to a decimal number, or rather to a base 10 structure. We can multiply each bit in the binary number by the corresponding power of 2 and sum the results. So we get 128 plus 64 plus 32 plus 8 plus 4 plus 2, which gives us 238. So 11101110 in binary equals 238 in decimal. Okay, why does binary work so well? The beauty of binary is that it's simple. It only uses two choices, on or off, which is equivalent to 1 or 0. Computers are built with electrical circuits that can easily represent these two states. It is like using a light switch. If the light is on, it represents a 1. If it is off, it represents a 0. This simplicity is actually very powerful. It makes it easy to build circuits that are both fast and reliable. So how does a computer work with binary? Let's start with memory, which is used for storing information. Inside your computer, there are memory chips, which act as a giant filing system that can hold only two options, either 0 or 1. When we save a photo, a document, or a song, the computer is storing that information as a long string of these zeros and ones. Then we have the processor or CPU, which is the brain of the computer. It performs all the calculations and decision making. Imagine the processor as a super fast worker who can only think in zeros and ones. For example, when the computer wants to add two numbers, it takes those two numbers, breaks them down into zeros and ones, and performs the math based on those values. And we also have input and output mechanisms whereby we can get data in and out of our computer. Let's take the example of typing A on a keyboard. When you type on a keyboard or click your mouse, you're giving the computer input. The computer receives the binary information. It translates it into ASCII, which is a way of representing characters such as A in binary form, and converts the output into a format that humans can understand, such as the image of the character A on the screen. Okay, let's look at hexadecimal. Hexadecimal or hex is a base 16 number system, meaning it uses 16 symbols to represent numbers. So instead of stopping at 9 like the decimal system, which is base 10, hexadecimal includes 6 extra symbols, which are A, B, C, D, E, and F. And why do we use hexadecimal? Hexadecimal is a shorter and more human-friendly way to represent binary numbers, which can get very long and hard to read. Since every hex digit represents 4 bits, it is much easier to work with hex in systems like programming, memory addresses, or colors and design. The following table summarizes the link between binary, hexadecimal, and decimal. So the decimal number 12 can be written as C in hexadecimal and as 1100 in binary. One common use for hexadecimal is to define colors in web design and digital graphics. Take the hexadecimal color code #FF5733, which uses 6 characters to represent a color. The first 2 characters FF represent the red component, which is 255 in decimal, and the next 2 characters 57 represent the green component, which is 87 in decimal, and the last 2 characters represent the blue component, which is 51 in decimal. And note the hash sign at the start. It is used to indicate that the preceding number is written in hexadecimal format. So far, we've learned about how computers use binary, decimal, and hexadecimal to represent numbers. But computers do more than just work with numbers. They store and process text, images, and more. So the question is, how does a computer understand text like A, B, or even a smiley face emoji? That's where encoding systems come in. In IT, encoding refers to the process of converting data into a specific format so it can be efficiently stored, processed, or transmitted. Without a universal encoding standard, systems would fail to interpret characters consistently, leading to corrupted text and communication errors. The most common encoding standard is ASCII, which stands for American Standard Code for Information Interchange, and it maps characters to binary values using 7 bits. This means it can encode 128 unique characters because 2 raised to 7 bits gives us 128 range of values. It covers uppercase and lowercase letters in the English language, numbers, common symbols, and control characters like new line and tab, which is similar to pressing enter and tab keys on the keyboard. For example, in the ASCII character encoding standard, the uppercase letter A is assigned the decimal value 65. This means that when a computer stores or transmits the letter using ASCII, it uses the number 65 to represent it. This decimal value can then be represented in other number systems. The decimal value 65 is equivalent to the binary number 01000001. This is how a computer internally stores and processes the character A. The decimal value 65 is also equivalent to the hexadecimal value 41, which is often written as 0x41, where the 0x prefix indicates its hexadecimal. So, hash and the 0x prefix can indicate hexadecimal numbers. ASCII is great, but it's limited to 128 characters, which is not enough for all the symbols, characters, and scripts used around the world. To solve this problem, Unicode was developed. Unicode is a much larger and more flexible system that can represent text from virtually every language along with symbols, emojis, and more. It assigns a unique number called a code point to every character or symbol. Code points are written as U plus and the hexadecimal value. So U plus 0041 for the character A. Unicode supports over 1.1 million characters covering scripts from languages like Arabic, Hindi, Japanese, more, tons of emojis, mathematical symbols, music notes, and other specialized symbols. To store and transmit Unicode characters, we use specific encoding formats like UTF-8. UTF-8 uses 1 to 4 bytes per character depending on the character's complexity. So for example, the letter A takes 1 byte in UTF-8 and the smiley face emoji takes 4 bytes in UTF-8. Computers don't just process text, they can handle complex multimedia data like images, sound, and video. Despite their complexity, all of these media types are ultimately stored and processed as binary data. Let's first look at how images are stored in binary. An image is essentially a collection of tiny dots called pixels, which is short for picture elements. The image is divided into a grid of pixels. What we have on the screen is a 5x5 resolution image with 25 pixels. Each pixel has a color, and computers represent that color using numbers. We can see a black square within our image. Let's say 1 represents a black box, which is a part of the square, and 0 represents a white box, which represents empty space. So numerically, we could represent the image in ones and zeros like what we have on the screen. A high definition image would be a 1920 by 180 image, which has around 2 million pixels. The resolution defines the level of detail in the image. The higher the resolution, the more pixels it contains. Colors are represented using the RGB model: red, green, and blue. Each pixel has 3 color values, one for red, one for green, and one for blue, typically stored as 8 bits or 1 byte each. So for example, a bright red pixel might have an RGB value of 25500, which is the decimal representation. In binary, each color component is represented as 8 bits or 1 byte, which would be like this. And we've already seen that one hexadecimal digit represents 4 bits. Therefore, each RGB color component can be represented by 2 hexadecimal digits, which would look like this. And as seen previously, the entire RGB color is often written as a single hexadecimal string, such as hash FF0000 with the hash sign in front to denote it's a hex number. Images are often compressed to save storage space using formats like JPEG or PNG. JPEG uses lossy compression, meaning some image data is discarded to achieve smaller file sizes. This can result in a loss of image quality, especially with high compression ratios. PNG uses lossless compression, meaning no image data is lost. It finds patterns and encodes them efficiently without discarding any information. This results in larger file sizes than JPEG, but maintains image quality. Next, let's look at how sound gets stored in binary. Imagine a sound wave going up and down on this graph, where we have the sound amplitude or loudness on the y-axis and time on the x-axis. Sound is recorded by sampling the sound wave at regular intervals. Each sample is represented as a binary number. The more samples per second, which is the sampling rate, and the more bits per sample, which is the bit depth, the higher the sound quality. And formats like MP3 or AAC compress audio to reduce file size. And lastly, we have videos. Videos are basically combinations of images and sound. Remember how we discussed images being composed of pixels, each with RGB color values represented in binary? Well, video is essentially a rapid sequence of these images known as frames. Think of a flipbook. Each frame is stored just like a still image with its pixel data encoded in binary. The speed at which these frames are displayed, measured in frames per second, determines the smoothness of the video. Higher frame rates create a more fluid and realistic viewing experience. So just as each pixel in a picture is represented as binary, so is each pixel in each frame of a video. Video isn't just about visuals. It also includes synchronized audio. As we learned in the previous slide, sound is captured by sampling the audio wave and representing those samples as binary numbers. In video, this audio stream is interwoven with the video frames, ensuring that the sound aligns perfectly with the visuals. You can think of the audio track as a binary file running in sync with the binary image files that make up the frames. Video files are inherently large due to the sheer volume of image and audio data that they contain. To make them manageable for storage and streaming, video compression is essential. This is where codecs, short for coder-decoders, come in. Codecs are software or hardware tools that compress and decompress digital data. Codecs like H.264 use sophisticated algorithms to reduce file size. These codecs are lossy, meaning some data is discarded to achieve smaller file sizes. The degree of compression affects the overall quality of the video. Finally, the compressed video and audio streams are often packaged into container formats such as MP4, which allows for consistent playback across different devices. By breaking down images, sound, and video into binary, computers can store, process, and transmit them efficiently. Computers store and process data using standard units. First, let's look at storage. Data storage is measured in units based on binary prefixes. The smallest unit of data is a bit, which you've already learned, followed by larger units. 1 byte is 8 bits. Next are kilobytes or KB, which is about 1000 bytes, which is enough for a small text file. Then we have megabytes or MB, which is about 1 million bytes, typically used for images and short videos. Gigabytes or GB are about 1 billion bytes, enough for a high quality movie. And we have terabytes or TB, which are about 1 trillion bytes, commonly used for large business databases. Now let's talk about processing speed. Computers perform calculations at incredible speeds measured in hertz, which refers to the number of operations per second. Modern computers operate in gigahertz, meaning they process billions of operations per second. This processing speed directly impacts a business's ability to analyze data, execute complex applications, and complete transactions efficiently. High processing speeds enable faster data analysis, quicker response times, and improved overall productivity. Alright, we've covered a lot of ground today. Let's quickly recap the essentials. Data is everywhere. Think of it as the fuel powering modern businesses. Every customer click, every transaction, every social media post, it's all about data. Data needs structure and governance. Raw data is like a messy toolbox. We need to organize it, for example, structured versus unstructured, manage its life cycle, and govern it with rules and policies to make it useful. Data turns into insights. Business intelligence tools help us transform data into actionable insights, helping us make smarter decisions. Computers speak binary. At its core, data is stored and processed as zeros and ones. Understanding this helps us understand how computers handle everything from text to videos. Encoding is key. Encoding systems like ASCII and Unicode allow computers to understand and display text from all over the world. Multimedia is binary too. Images, sound, and video are all broken down into binary data for computers to process. And units matter. From bits and bytes to terabytes and gigahertz, understanding units of storage and processing helps us grasp the scale of modern data. So what's the bottom line? Data is a powerful tool. By understanding its fundamental concepts, you can leverage it to drive better business outcomes.